Now, so this is just a helpful sort of visual representation as a network of what's going on here. Okay. Now, we need to learn the nonlinear parameters, which are the centers, and the weights Wg. Okay. And we made the observation that if you fix the centers, then this is just a linear model, and we can use our linear model algorithms. Okay. In order to fix the weight, we need to fix the centers. Okay. And in order to fix the centers, okay, we're going to use this motivation as our way of fixing the centers. So how do we fix the centers? So step one, fix the centers to the centers of clusters in the data. And we saw an algorithm last time for finding the centers of clusters that are well separated and tight. Okay, so that's the idea here, that my centers are representing sort of clusters in the data, and the bump on that center is representing how that cluster of data affects the output, the final output at a test point X. Okay? And so, this is an unsupervised step. So this is an unsupervised step. Okay. So yes, it does depend on the data. Okay. So where you put your centers does depend on your data. So for example, to fix the centers, we can use Lloyds algorithm. Okay. Where, and the way the Lloyds algorithm started was pick a random center for your first center, and then pick the point that's furthest away, and then pick the point that's furthest away from those two, and then pick the point that's furthest away from those three, and so on. Okay, so there's this Lloyds algorithm that we discussed last time. Okay, so pick the centers, it's unsupervised. So while yes, it does use the data, it doesn't use the Y values in the data. It doesn't use the Y values in the data. So you're not really fitting the data. You're just fitting, the data, the distribution of the inputs. You're finding the clusters. You in an unsupervised way, you are, using the data to get the cluster centers. So it's not a heavy level of fitting of the data. Okay, we're just finding clusters. And you might wonder, well, how do we know we found the right clusters and so on and so forth? It's not so important. Okay, because these μj's, these centers, are only the first step in the radial basis function. Okay, you still have the flexibility to set the heights of the clusters, and that's where most of your power in fitting the data comes. That's where you're going to look at the Y values. So once you have fixed the centers, okay, so this fixes the centers. Okay, then you have a linear model. Okay, with weights W0, W1 up to Wk. And so you can use whatever linear model algorithm you want for your application. Okay, so you have a linear model with similarity features. Okay, where your feature for an input X is just the K similarities to your K centers, which you have fixed using Lloyd's algorithm. And now you have a linear model with weights W and WK, and you can use whatever linear model algorithm you want, depending on your application. So you can use PLA/pocket if you're doing classification, the pseudo-inverse algorithm. Okay, so pseudo-inverse, so this is classification. You can use the pseudo-inverse algorithm for regression, or you can minimize the cross entropy error, so gradient descent and the cross entropy. I'll just call that CE for cross entropy for logistic regression. Okay. And so this is the radial basis function network. Very nice algorithm. So let me summarize one last time, and then we're going to go and look at results. Okay. So the radial basis function network is a linear model modulo the selection of centers. Okay. So visualize. You're going to place bumps at certain locations in the space. These locations in the space should represent the data. So you pick these locations in the space as centers of the clusters, and if you're choosing K centers, then you want K clusters. So you run Lloyd's algorithm to get these K centers. Okay, so you pick k prototype points. Okay, and now for an input x, you compute the similarity to each prototype center. What is the similarity? It's my kernel that takes as input the distance to the center. Okay. And then you combine your features in a linear model. Okay. And these weights correspond to the heights of the bumps at each of the centers. Okay. One more thing. You have to pick R. So how do we pick R? And we go back again. Okay, so we could pick R with cross-validation, but again, R is the scale parameter. And remember, what are the purpose of the bumps? The purpose of the bumps are to represent your data. So you have k bumps. Okay, so picking R. Okay, so you have k bumps in d dimensions. Okay, so if the radius of the data is r, let's say 1, okay, so then the volume of a bump, the volume covered by a bump is roughly r to the d, okay, and since there are k bumps, the volume covered by all the k bumps is k times r to the d, okay, and you want this to, roughly speaking, cover the whole data set. And if the whole data set has a bound of r, then this should be approximately the size of the data. Okay, so this tells us, okay, roughly speaking, that R should be approximately k. So the scale parameter R for the bumps should be approximately the radius of the data. Sorry, this is R to the d. Should be approximately the radius of the data divided by the dth root of k. Okay, so basically proportional to k, the dth root, 1 over the dth root of k. Okay, so here's a rule of thumb for picking the radius, the scale parameter R. So now we can pick the scale parameter R, we can pick the centers. So these become well-defined similarity features, and you just have a linear model in a feature transform space that consists of, similarities to k prototypes, okay, where distance, and we have even a heuristic for picking the scale parameter. Okay, so now let's look at some, results, some illustrations. Okay, so we're looking at the same data that we showed with the nonparametric RBF, okay? And now we're using the parametric RBF network, and on the left we have 4 centers, so we've placed these 4 centers, you can see them in gray, okay? And now, after we place the 4 centers, we've picked R as 1 over k because in one dimension, the heuristic is, 1 over k to the 1 over d, okay? So we're picking R equals 0.25, okay? And now, okay, we run the linear model. So we use the pseudo-inverse algorithm to produce the weights, the bump heights. Okay, and now when we add up the bump height, we get this blue curve, which is a pretty decent fit to the target function, which is this light gray curve. Okay, on the right, same experiment, but I've chosen 10 bumps now. Okay, so we place the 10 bumps. Okay, R is 1 over k, so R is now smaller. Okay, we compute the similarity features, and then we run the linear regression, the pseudo-inverse algorithm, and we can clearly see overfitting. The blue curve is not a good approximation to the light gray target function. So this is clearly overfit. Okay, so what can we do about this overfitting? Well, the obvious answer is choose fewer bumps, and that was why we went from n down to a fixed number k in the first place. Well, here even 10 bumps is too many. Okay, you're overfitting. So choosing the right number of bumps, choosing the right number of clusters in your data. Okay, that's an open question, and there's a lot of research on that. Okay, and you can certainly use cross-validation as a tool for selecting the number of clusters, the number of bump centers. Okay, or you can realize that, well, what's the reason for this overfitting? It's true, we have a fairly complex model, but it's overfitting, it's fitting the noise. Okay, so we can regularize, we know how to do regularized linear regression. Okay, so we can regularize the linear model and stay with 10 bumps. And let's see what happens when we do that. So on the left is the original 10 bump radial basis function network. On the right is the same 10 bump radial basis function network with the same centers. Okay, and once you fix the centers and once you fix the scale parameter, it's just a linear model. So we run regularized linear regression and look at the huge difference. Okay, so regularization, our old friend, our foundations coming back. Okay, but it's a totally new model. It's the radial basis function network, but we know the linear regression part that comes after you fix the centers and after you have fixed your scale parameter, the linear regression part has to be regularized, otherwise you'll overfit. And this allows us to use 10 bumps, okay, providing we use regularization. So that mitigates the need to choose exactly the right number of bumps, exactly the right number of clusters in the data, if you choose, the right lambda, the right amount of regularization. And either way, you have to pick a parameter. Either you fix k equals 10 bumps and regularize, or you need to carefully choose the number of bumps. Okay, so let's summarize, the radial basis function network. Okay, so we derived the nonparametric radial basis function as a soft generalization of the k nearest neighbor. Okay, there are many ways to derive radial basis function networks and radial basis functions. You can derive them from regularization theory, from noisy interpolation theory. We did it as a soft extension of the nearest neighbor. Okay, and as we saw, there's the parametric version and the non-parametric version. The non-parametric version is heavy because you have to carry around the data. It's heavy both in terms of memory and in terms of computation. The parametric version reduces the problem to storing just the n bump heights, okay, but then you still need to store all the data to compute the similarity features for a new input, so it's still heavy. But then we reduced the parametric RBF to the parametric RBF network, okay, and that does two things. It reduces the computational challenges from only having to store the centers for k bumps and the weights for those k bumps, okay, and it also helps with the overfitting issue. Okay, now, given the centers, okay, it's easy to learn the weights. That's just a linear model. Okay? So basically what we have developed here is the next level of complexity, where we have sort of developed the linear model with an adaptable feature transform. The feature transform is dependent on where you place the bump centers. In other words, to which data points, to which prototypes do you compute similarities. Okay? And that it turns out that when you have adaptable feature transforms, that's a lot of power, and we'll see that when we talk about neural networks. But for the moment, this adaptable feature transform is not as powerful as it could be, because we're not doing a full fit of the centers to the x's and the y's. We're just picking the centers based on the motivation that they're bump centers that represent the data. So we just pick the bumps to be centers of clusters in the data. So the bumps are selected in an unsupervised way, so they don't in any essential way overfit the y values. Okay. Now, a couple of comments. The first comment is that we assume that the bumps are spherically symmetric. Well, you can have different shaped bumps. That corresponds to choosing a covariance matrix for the Gaussian kernel. So we won't get into those details. The second is that are there ways to choose better centers? Okay, and so now we have seen unsupervised learning twice. We saw it in the previous lecture as a technique for storing the data in such a structure, clusters, such that branch and bound becomes efficient. So it's efficient to search for nearest neighbor. So unsupervised learning, organizing the data in these specialized structure revealing ways can help algorithmically. But now we see that it also is a pre-processing step for the radial basis function network. You need to put your bump centers at centers of the clusters in the data. Okay, so this suggests that unsupervised learning is important not only as a sort of organizational tool, a pre-processing tool for supervised learning, but we've already discussed it as an important, standalone task. Okay, so why don't we spend a little bit of time next lecture, touching on unsupervised learning. Okay. And just to show you some of the power of unsupervised learning, here's just a quick peek. Okay, so I showed you this multi-class version of the digits data where we use the nearest neighbor algorithm in the multi-class mode. Okay, and we get this, this very nice, elegant separation of my space into the various digits, 1, 0, 2, 8, and so on. Okay. Now, supposing you don't know the digit values, I just show you the symmetry intensity values for all the data. So you can do it, you can run a 10 clustering. And so on the right, I'm showing you a 10 clustering of the data. Okay, so if you've done a good clustering, look, there's so much structure revealed by a 10 clustering. And look at how this structure of the 10 clusters, mimics the supervised classification regions. Okay, so it just shows you the power of clustering. And, if we already started with, clusters that look like this, then by placing a center at each of these, clusters, probably the radial basis function network will do a fantastic job at classifying the digits. Okay, so what we'll do next time is study this diagram on the right a little more carefully, or we'll study algorithms for coming up with good clusterings of the data. And in general, optimal clustering is a hard problem. Okay, but we'll talk about that next time. For now, we're checking out. Ciao.